Okay, number 275, find and identify any stationary points for this thing here. Now there's an exponential in here, that gets interesting. For what values of x is the function concave up? So that's this thing here, that's concave up, whereas that there is concave down. And points of inflection where the two concavities change. Okay, so let's cheat. You can cheat one way by looking at here, but call me lazy, but this is definitely more efficient. We can see here's the exponential ex minus 4x plus 2, and Desmos straight away has told me that there's a minima at 1.386, and its corresponding y point is 0.45. So that's where the tangent line would be. The gradient would be 0 passing through 0.45482 there. And also the answer, that is all concave up. Any value of x will be concave up. So we've already answered this bit here, but let's just answer that now. Let's say for this, call that question A, call this part B. This one here is x encompasses real numbers. That's code enough to answer that. So any x value will be showing that it'll be, the curve will be concave up there. So to find and identify any stationary points. So let's remind ourselves of that's an XY coordinate point, and is it a maximum, minima, or points of inflection? Don't forget, inflection points could be have a zero gradient there. Right, so what we need to do is simply differentiate, and that gives us ex minus 4. We need to solve this, put this ex minus 4 equal to 0. So ex equals 4. And if we take the natural log of both sides, that's going to cancel that out. So there is the value. And officially that is 1.386. We'll just call that 1.386. So that's the x coordinate. Let's find the y coordinate first. If I plug in 1.386 into this function here, so that's like saying natural log 4, isn't it? Okay, that's the shorthand for that. Minus 4 times natural log 4 plus 2. That there cancels out to be 4. 4 minus 4 natural log 4 plus 2. And if I'm cheating, it will be 0.4548. 4dp there, just to be consistent. So we've now got our coordinate point. We know it's a stationary point, but now we need to identify it. How do we identify it? Well, what is it? It's a minima. Okay, so, but you can't just say on my graphing calculator in the exam, it's a minima. Okay, so you've actually got to show it algebraically. So what we're going to do, one option is you could show a gradient slightly below this, that's what, 1.3. So if you said 1, the gradient there is negative. On this side here, just above it, say 2, the gradient's positive. So that obviously shape confirms that it's a minima. But the quickest way, the more efficient way, is the second derivative test. So differentiate twice. So differentiate this, it's just ex. So plug in your value, natural log 4 equals e natural log 4, and that is positive. So therefore, at x equals natural log 4, function, you just say is a minimum. That's probably okay. So by the second derivative test, we've put in the stationary value position at x, and it's come out to be positive. Therefore, at that point is deemed to be a minima. Okay, so we have just answered the question there. Let's just check that we should do this process. If we do check on New Lake here, it's always a good idea. And here we have it. So that's the first order derivative. We had that. Put that equal to 0. Therefore, x equals natural log of 4. And there's our y coordinate. And it's concave up for all x. And how have I shown that? I've said x encompasses R point.